Hello everyone, my name is Li Zhou. My presentation is using t-SNE for visualization. Before my presentation, I should say thanks to my professor, Dr. Luis Ruda, for his great help and guidance. In my presentation, I will introduce some basic knowledge of dimensionality reduction and comparison. Then I will present SNE in detail as a basis of t-SNE. After that, I will tell you how t-SNE different from SNE and its effectiveness of visualization compared to other methods. Dimensionality reduction is to convert the high-dimensional dataset into a 2 or 3-dimensional space that can be displayed in a scatter plot. When confronted with the curse of big data, we can use dimensionality reduction algorithms to make the data get to the point. In this example, there are 4 datasets. A is the genomics mouse brain dataset. B is the hippocampus dataset. C is the melanoma dataset. D is the mouse retinal bipolar neural cells. They have up to 1.3 million cells. However, with the help of dimensionality reduction, it is clear to show how many cell types and the relationships among all the organs, which can contribute to the medical research. As we all know, there are 2 kinds of dimensionality reduction. The first one is linear dimensionality reduction. That means given n d-dimensional data points x and a choice of dimensionality r is less than d, optimize some objective f sub x of n to produce a linear transformation p, and call y is the low-dimensional transformed data. Here, P is the eigenvector matrix associated with M. In this table, it shows several dimensionality reduction methods, in which PCA is to minimize the sum of the squared residual errors between projected data points and the original data points. PCA minimizes low-dimensional reconstruction errors. But another sensitive objective is to maximize the scatter of the projection. So it would yield the most informative projection, which enables it to preserve the global structure well. In this figure, because the classes are far from each other, so in the low-dimensional space, the global structure are still well. But we can't see the within class structure clearly. MDS seeks to maximize pairwise distance in dimensional space and minimize classical Shepherd scaling. The purpose of LDA is to project data in such a way that separation between classes is maximized. It seeks the projection that maximizes between class variability while minimizing within class variability. Therefore, LDA is good for preserving the global structure, but the local structure will lost after dimensionality reduction, the same as PCA. Another one is nonlinear dimensionality reduction. When data points in high-dimension space are linear, it is efficient to use linear methods to visualize them in a lower dimension space. But for those that can't be linear separable, then linear methods can't perform well. For this purpose, nonlinear methods are suitable to reduce the dimensionality and describe the structures among the data points. Generally, nonlinear methods can keep the low-dimensional representations of very similar data points close together. For example, the left picture is a sphere in a 3-dimension space. It can't be separated well using many lines. PCA doesn't work well because it can't cluster data points according to the similarity described in similar colors. But using nonlinear mapping or embedding, such as Italy, isomap, t-SNE, the structure can be visualized better. In most cases, most of the nonlinear methods can't preserve local structure and global structure at the same time. Now, let me introduce several nonlinear methods. The first one is kernel PCA. It is one of the most classical methods. It is the extension of PCA and enable PCA to classify nonlinear data by mapping data to a higher dimensional space to find a linear separable pattern in the new feature space. In the mapping step, there are different kernels can be used, such as polynomial or Gaussian, according to the different data distribution. And then use PCA to do the projection in the low-dimensional space. That means it finally converts the problem to compute principal components by solving eigenvalue problem. In the circle datasets, it is obvious that KPCA outperforms PCA. So what about Italy? It has a user-defined key nearest neighbor. Let's say k equals 5. Then it will find the 5 nearest neighbors xj around xi. In this picture, xi is a red point. And given the condition that the sum of the weights is 1 and the xi minus the weighted sum of neighbors is minimal, then we can calculate the weight vector wij given sample xi. For the n samples, it has a weight matrix. Then we can use this weight matrix to embed the data points in the high dimensional space to a low dimensional space. Actually, it will convert the problem to an eigenvalue and the eigenvector problem as PCA does. But this time, the difference is that it will choose eigenvectors corresponding to the bottom eigenvalues. The result will look like this. The weight in the low-dimensional space is the same as that in the high-dimensional space. So, Italy can preserve the local structure well. ISOMAP seeks a lower dimensional embedding, which maintains geodesic distance between all data points. It constructs a weighted graph at first. The weights can be calculated as the distance between two data points. If they are very close, then the path will be chosen as the shortest path. If they are far from each other, then it will use the Kajra or Floyd's algorithm to calculate the shortest distance. Like in this picture, A is far from B. They would be connected directly. It will start from A to find a point C, which is very close to A, and start from C to find another data point D that is very close to C, and so on, until A reaches B. Then the sum of the weights will be taken as the shortest distance between A and B. In this weighted graph, data point C can be connected to Xi by this path with a weight of 0.5, or by this two paths with the sum of the weights of 0.4. Because the sum of the weights of these two paths is smaller, they will be chosen as the shortest path between C and Xi. Then it will find the key nearest neighbor. Let's say k equals 3. Then xj, c, and d will be chosen as the neighbors of xi. And e and f were taken as not connected to xi. Now we can get a squared distance matrix. Then it will apply the eigen decomposition to find the top eigenvalue and keep the maximal information of the data points like MDS do. So it will keep the global structure well. In ISOMAP, there are many holes. It because the shortest path between two data points are not the paths connected them directly. Like in this picture, the red path replace the blue line as the path between the two data points. t-SNE maps the data points in the high-dimensional space to a low-dimensional space according to their pairwise distance. It introduced gradient descent to learn and minimize the Kullback-Leibler divergence between probability density of the high-dimensional data points and the low-dimensional data points to preserve both the local structure and the global structure. The figures shows the results of applying t-SNE, thermal mapping, isomap, and Italy to the elevated phase dataset. Again, isomap and Italy produce solutions that provide little insight into the class structure of the data. The map constructed by the thermal mapping is significantly better since it models many of the members of each class very close together. But none of the classes are clearly separated in the thermal map. In contrast, t-SNE does a much better job of revealing the nature classes in the data. Some individuals have their 10 images split into two clusters, usually because a subset of the images have the head facing in the significantly different direction or because they have a very different expression or classes. For these individuals, it is not clear that their 10 images form a nature class when using Euclidean distance in pixel space. So in the following part, we will introduce how t-SNE works. Because t-SNE is an extension of SNE, so we'll introduce SNE at first. Stochastic neighbor embedding, we also call it SNE. It was introduced by Hinton and Rorris in 2022. It starts by converting the high-dimensional Euclidean distance between data points into conditional probabilities. For data point xi, it will find its similar data points by calculating the Euclidean distance and use the conditional probability function to see whether they have a high probability. For nearby data points, they have very high pairwise similarity. For those that are far from xi, they will be chosen as the dissimilar data points. Because we are only interested in modeling the pairwise similarity, we set pi given I as 0. There are three different classes and you can easily distinguish them from each other. The first step in SNE is to create a probability distribution that represents similarities. We have picked one of the points from the dataset. Now, we have to pick another point and calculate Euclidean distance between them. Then, we generate Gaussian distribution centered at xi. Here, we ignore the sigma for now and assume we have already decided what it should be. After calculating the first point, we have to do the same thing for every single point over there. Now, we can distinguish between similar and dissimilar points. Finally, we can calculate the sum of the conditional probabilities given the point xi, and so on. We can calculate all of the conditional probabilities of all the data points, and the sum should be 1. Here, we should remember that pj given I is not the same as pi given j. The second step is to generate the Gaussian distribution in the low-dimensional space. Here, yi and yj is the low-dimensional mapping of the data points in the high-dimensional space. We can compare these two conditional probability functions, and we can find that they are very similar. The only difference is the value of the sigma. In the low-dimensional space, it has a fixed value of sigma of squared root of 2 over 1. If yi and yj perfect models the data point xi and xj, the conditional probability should be the same. SNE introduced the Kullback-Leibler divergence to measure how well the data points in the low-dimensional space model the data points in the high-dimensional space. In mathematical statistics, the Kullback-Leibler divergence is also called the relative entropy. It's a measure of how one probability distribution is different from a second reference probability distribution. The figure illustrates the relative entropy for two normal distributions. If we know the conditional probabilities both in high-dimensional space and the low-dimensional space, given the data point xi, then we can use this formula to calculate the Kullback-Leibler divergence, and our purpose is to minimize the result. t-SNE introduced a closed function to calculate the Kullback-Leibler divergence of all the data points, in which Pi Qi represents the conditional probability distribution over all other data points given data point xi in the low-dimensional space and the high-dimensional space. When we use small conditional probability in the low-dimensional space to model the conditional probability in the high-dimensional space, it will cause a high cost. So the cost function is focused on retaining the local structure of the data in the map by choosing a suitable sigma. It is clear in the fig. In these regions, a small sigma is better than a big one. Then how to choose a good sigma? t-SNE introduced a perplexity. It is defined by the user. When the perplexity increases, the sigma will increase too. It performs the binary search for the value of the sigma and produces a Pi. It uses channel entropy, so we can say that perplexity is a smooth measure of the effective number of neighbors, and its typical value is between 5 and 50. t-SNE applied a gradient descent to minimize the sum of the Kullback-Leibler divergences between the conditional probabilities in the low-dimensional space and the high-dimensional space. It is initialized randomly from an isotropic Gaussian with poor local minima to help find the global minima or avoid stopping at the local minima or settle. It used a large momentum in the learning step. In this formula, solution at t iteration equals solution at t minus 1 iteration, plus the learning rate times the current gradient, and added to the momentum at t iteration times the solution at t minus 1 iteration minus solution at t minus 2 iteration. In the beginning, for every data point in the low-dimensional space, the sigma of the Gaussian distribution centered at yi will be changed to get a different exertion on yi. Yi will move towards data points with high pairwise similarity in the high-dimensional space and away from the dissimilar data points until it reaches the global minima. Then the learning step will stop. Stochastic neighbor embedding has two problems. The first one is that it is difficult to optimize. That because Kullback-Leibler divergence is not symmetrical. It makes the optimization complex. Another problem is that the crowding problem, because the Gaussian distribution, the probability is infinitesimal. The data points that are far away from the center of the data will lose the force on the spring between it and the data points far away, makes them crowded together. Now let's look at the formulas in t-SNE. The cost function is still a Kullback-Leibler divergence, but this time it used the joint probability instead of the conditional probability to make it symmetrical. In high-dimensional space, it defines the joint probability as the mean of the conditional probability j given I plus the conditional probability I given j. In low-dimensional space, it introduced the student t distribution and normalized it. So in gradient descent, it can only consider Qij because Pij is a fixed value here for reference. Whereas in t-SNE, it has to consider Qj given I and Qi given j. So in t-SNE, it is easier to normalize Now let's take a close look at the gradient descent. Yi minus yj can be seen as the spring between yi and yj. This part in the red box is an exertion or compression on yi. It decides the direction of the force on the spring. That means to repulse or attract. The left figure shows the data points in the high-dimensional space. The right figure is the probability distribution in the low-dimensional space. Because SNE and t-SNE both use a random walk algorithm to map data points in the low-dimensional space. If the data point has a high PLY similarity in the high-dimensional space but has a low similarity in the low-dimensional space, let's say this red data point, it will have a strong force on the spring to attract Yi to move towards it. If the data points have a low similarity in the high-dimensional space, but have a high similarity in the low-dimensional space, let's say this blue data point, then the spring force is big and the exertion is positive, which means it will add a repulsion on Yi. If they have a high similarity both in the high dimensional space and the low dimensional space, let's say this red data point, then the exertion is positive and the force is small, which means Yj will attract Yi, but not so strong. If they have small similarity both in the high dimensional space and the low dimensional space, let's say this orange data point, it will exert a repulsion on Yi. But the difference is that the force on the spring is much bigger in student T distribution than in Gaussian distribution because of the heavy tail. This will let the data points move far away much more than in the original space. Obviously, in Gaussian distribution, if the data points far away from each other, then the similarity goes to infinitesimal. So the data points will do like this. And this is the solution to the crowding problem. The figures shows the gradients between two low-dimensional data points, Yi and Yj, as a function of their pairwise distance in the high-dimensional and the low-dimensional space. The positive values of the gradient represent an attraction between the low-dimensional data points, Yi and Yj, whereas negative values represent a repulsion between the two data points. From the figures, we observe two main advantages of the t-stochastic neighbor embedding gradient over the gradients of the stochastic neighbor embedding. First, the t-stochastic neighbor embedding gradient strongly repel dissimilar data points that are modeled by a small pairwise distance in the low-dimensional representation. Stochastic neighbor embedding has such a repulsion as well, but its effect is minimal compared to the strong attractions airways in the gradient. Second, although t-stochastic neighbor embedding introduces strong repulsions between dissimilar data points that are modeled by small pairwise distance, these repulsions do not go to infinity. That means if two data points in the high-dimensional space are far away from each other, then when they are projected to the low-dimensional space, they will move much too far away from each other. Taken together, t-stochastic neighbor embedding puts emphasis on modeling dissimilar data points by means of large pairwise distance and modeling similar data points by means of small pairwise distance. This is the algorithm of the t-SNE. In the first step, it will compute the PLY similarity in the high-dimensional space with a user-defined perplex using channel entropy. Then calculate the joint probability Pij. After that, it will use random walk to initialize the data points in the low-dimensional space. We say it initial solution. Then, in the learning step, for each iteration, it will compute the joint probability in the low-dimensional space and the gradient, and applied an initial learning rate and a user-defined momentum to speed up its optimization until it finds a global minimum. This is the visualization of a Core 20 dataset. We apply the t-SNE, thermal mapping, isomap, and LLE. For many of the 20 objects, t-SNE accurately represents the one-dimensional manifold of viewpoints as a closed loop. For objects which look similar from the front and the back, t-SNE distorts the loop so that the images of front and back are mapped to nearby points. For the 4 types of Toyer car in the Core 20 dataset, the 4 rotation manifolds are aligned by the orientation of the cars, so to capture the high similarity between different cars at the same orientation. This prevents t-SNE from keeping the 4 manifolds clearly separate. It also reveals that the other 3 methods are not nearly as good at clearly separating the manifolds that correspond to very different objects. In addition, isomap and LLE only visualize a small number of classes from the Core 20 dataset. Because the dataset comprises a large number of widely separated submanifolds that give rise to small connected components in the neighborhood graph. Again, we apply the t-SNE, thermal mapping, isomap, and LLE on the mixed dataset. The results reveal the strong performance of t-SNE compared to the other methods. In particular, thermal mapping constructs a ball in which only 3 classes representing the digits 0, 1, and 7 are somewhat separated from the other classes. Isomap and LLE produce solutions in which there are large overlaps between the digits classes. In contrast, t-SNE constructs a map in which the separation between the digits classes is almost perfect. Moreover, detailed inspection of the t-SNE map reveals the much of the local structure of the data, such as the orientation of the ones. This is my presentation. Thank you for your time.